Welcome to problem solving session for the course Linear Algebra. I'm Siddhi Balgambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 5, that is problems related to basis of a vector space and dimension of a vector space. So let us start with our first question. So secondly, so let K be a finite field with Q elements, then the multiples m into 1k m in z for a subfield of k, and p that there exists a smallest positive natural number p such that p into 1k is 0. This 1 sub k denotes the multiplicative identity 1 of the field k. Yeah, for the books for this course, uh, you can follow any book from linear algebra. Uh, okay, yeah, there is this book. Uh, just a second. Yeah, there is this linear algebra book by Hoffman and Kunz. You can write that. I will write the name of the book later on in the chat. Is that okay? Yeah. So,
Excuse me, this
yeah.
is which question we are trying to solve in the week 5?
Okay. But this question is not there in the sheet. So I had access to the older assignments, and I picked this question from that sheet. But because I felt that this actually takes care of many concepts which we went through this week, so that's why I'm writing the question in detail so that you can refer this later on. Yeah.
Oh, thank you.
Yeah. Sure. So, moreover, it is prime, and then you can note this, then it is called the characteristic of K, and it is denoted by this notation char K. Okay, and the subfield K dash, which is defined by elements of this form m into 1k, contains exactly p distinct elements namely these elements 0, 1k, 2k, and p minus 1. Oh, sorry. This 1k, 2 into 1k, and p minus 1 into 1k. And C is show that Q is p power n, with n is here dimension of k over k dash. Okay, so this is what we need to prove. So I hope you understood the question. So K is a finite field given, and let me just write again. So K is my field, finite field, and this K dash is defined like, and it has then 1K is, let me just write it again. 1K is multiplicative identity of this field. And then this K dash is defined like all the, so it says M into 1K where M belongs to Z. So M into 1K, 1K such that M belongs to Z. So it is actually addition of this 1K M times. So it is just a collection of all the elements of this form. Addition of 1 M times where M is any Z. And any integer. So we have to prove that this K dash is a subfield of K. So our first question is to prove that this K dash is a subfield of K. So when we say subfield of K, it means we to prove that all this, first of all, it is contained in K, and secondly, that it forms a field. So first to check that it is subset of K. So it is anyway K dash is collection of all the elements of this form, right? If and since K is a field, this belongs to K for all M in Z. When we say M in Z, it means that since 1K belongs to this K, I mean, this makes sense for M positive, right? I mean, this for all M in, I can say, N. Okay, and for when M is less than 0 or negative, we know that for 1K in K, we have minus 1K, the additive inverse of this 1 in the field K. So when I write this M into 1K for this M negative, it is actually addition of this minus 1K M times. Okay, and again this minus 1 belongs to K, so this M into 1K again belongs to K. Therefore, this K dash is actually contained in K. So therefore, subset is proved. Now the additive identity. Now we have to show that, so additive identity is there in the K, in our original field K. But now I also need to prove that this additive identity is also in K dash. So So since k dash is all this m into 1k such that m in z, so v dot 0 belongs to z. So 0 into 1k will be my 0k here. So hence additive identity belongs therefore 0k. Therefore k dash has additive identity and okay. Now we need to check for multiplicative identity. So anyway for m is equal to 1, this 1 into 1k will be just 1k. And this 1k belongs to this k dash. So note that this belongs to k dash here. Okay, we need to show that this is element of k dash because 0k is anyway there in my original field. But we need to prove that it is there in this k dash, the subfield, which the subset which we are trying to prove that it is a subfield of k. So this k dash has this additive identity is what we proved here because anyway this all these m1k are elements of my uh, original field k, and this 0k is additive identity of field k. So anyway this m into 1k plus 0k will always be m1k because this addition when I'm writing here is actually happening in k. So this identity which we obtained here, this 0k, is the same identity as my original my field k, and we show that it's also in k dash and it satisfies all these property because of inherited addition from third is multiplicative identity. So we need to prove the multiplicative identity as well. So when I take m is equal to 1, this 1k, 1 into 1k is 1k again. And this 1k is now multiplicative identity of my original field, and it also in my k dash. So anyway, for any x in my original field k, this x into 1k will always be x. But now what I'm taking is I'm taking these elements of the form m into 1k in k dash, but these are also all the this is also element of my original field k. Let me write just one like this. And this m1k into this 1k will anyway give me 1 mk because this is now I'm looking at multiplication in k. So when we are saying that something is a subfield of my original field k, the addition and multiplication are from the original field, and we need to show that the subfield has additive identity and multiplicative identity, which are actually the multiplicative and additive identity of my original field. That's how we do for subspaces as well. The 0 in my original vector space V, and if I want to prove that something is a subspace, yeah, something is a subspace. So we show that the original 0 from my set is also there in my subspace. So yeah, that's it. And that's what we are trying to do. The 0 for the field, we have multiplication and addition. So 0 is the similar 0 we have here. And multiplicative identity is the similar 1k which we have from the set. Okay, and so now let us, so 1k we just proved. So now closure under addition. We have to prove, so addition, multiplication, and now the closure under addition. I mean, these are very routine checking for proving something is a subfield. But let us finish this, and then we will move to the second question, which actually takes care of so many things which we uh, learned in this week. So first, let us prove this one so that, so let M1K and N1K belongs to K dash. Their sum is this M1K plus N1K. Okay, and this, if you check, this will be M plus N 1K, because this distribution is inherited from my original field K. This distribution property of K. And but then this M and N are integers. This again becomes some integer, and this now belongs to my K dash. Therefore, this K dash is closed under addition. Okay. And fifth one is closed under multiplication. Again, we have to take let M1K and N1K in K dash, and this M1K into N1K is again M into C. M into 1NK will be this M into N, 1K into 1K. So we are in the field. So this 1K into 1K anyway will give me 1K, because 1K is a multiplicative identity. So this will give me, sorry, N into 1K. So this is some number into 1K is what we got. Uh, so therefore, this again some integer. And this shuffling and see how we could go from here to here in general. So this is not possible. So for example, if I had few elements xy for this xy into AB is equal to xa into yb does not make sense in general. Okay, so this is not true in general in a field. Okay, so the reason okay, because we are not given, so K is any field, we are not given that K is abelian field or any kind of field. We are just given that K is a field, but we could do this here because M into 1K is here, and this N into 1K, and what I'm essentially doing is this M into 1K, because associativity is there, that's not a problem. So I'm doing this, and then since this is multiplicative element, so whatever field, whether it is abelian or not, in general for any field, multiplicative identity, it commutes with the every element of that field. So when I'm writing this M1K and sorry, this M1K will be equal to 1km. Okay, so that's why this, from here I get this M1K into N1K as m into n 1k into 1k, and now I am combining these two. Because associativity, I can do the multiplication like this. And then this mn and 1k into 1k is anyway 1k. And now I'm getting what I got here. So this, combining this, like, so this, what I'm trying to say, that this to this is not that trivial as we think, or this to this, in fact. There are so many operations which are, and the properties of field and the multiplicative identities are taking place when we are doing all this. Okay, and now this sixth property. Wait, multiplication, additive inverse. Additive inverse we can check from here. So seventh is additive, sixth, I guess. Yeah, sixth is additive inverse. And so for m into 1k in k dash, this minus m into 1k will be minus m 1k. That's not uh, really special, but because this minus m into 1k plus m into 1k will be minus m plus m 1k, and this will give me 0 into 1k, and that is, we know, 0k. So therefore this minus of m1k is minus m into 1k. So note that these two are different. These two represent different things. I mean, they are equal, but what this means is this is additive inverse of m1k. And when I write this, this is how I defined the addition for negative here. So if it is, when I'm writing this, this is actually minus 1k m times. Okay, so I just wanted to point out that these two things, though they are equal, they actually represent, as a notation, they represent different things. Okay, so now seventh one is, yes, now this is the important property which we actually need to check. So this addition, multiplication, and all those things are inherited because of k being filled, and all the addition properties are followed because of we are only having this coefficient as integers and so on. Not the coefficient, I mean integer addition of 1k. But now this is something non-trivial which we will be proving for this question. So non-inverse of non-zero elements. So far whatever we proved, we nowhere used that our field k is finite. But this is the first time where we will be using that. So inverse of non-zero elements in k dash. And see, I mean, inverse will be there in k because k is a field. But now we have to prove that inverse exists in my field k itself, k dash itself. So note that the inverse for the element m into this m1k will exist in the field k, but we need to show here that this inverse, this multiplicative inverse. So when I'm writing the inverse, the multiplicative inverse, because we already okay, because we already discussed the additive inverse earlier. So we have to show that the multiplicative inverse exists in k dash. This is what we need to prove. That will give us that k dash is a field, and not only just showing that it has some inverse. Okay, so let m into 1k belongs to this k dash. And what we will do is we will just take this set. Okay, and m non-zero. Because if m is 0, then what we say? If m is 0, then this 0 into 1k is 0, okay? And we don't want to take, we are not discussing that. We want inverse of non-zero elements. So this m is non-zero. So we are taking this set. Let us add 1k to this set. Does not matter even if we don't. Okay. mk, m square 1k, m cube 1k, so on. So this is, in short, I'm taking this set. M into, sorry, m power, let us say t into 1k, 1k such that t belongs to n. So when I'm writing this n, this is from 0 to 0, 1 and so on. Okay. The reason being this and m power 0, 1k is just my 1k. Just for the sake of notation. And that's how it will be. No, he's not here. So m naught into 1k will be 1k. Yes. So note that but this k is a finite field. And k dash is a subset of k. Therefore, k dash is a finite set, right? We are given that. This is important information we have here, that k is a finite field. And this k dash is finite set. So, no, he's not here and he left for today. So, k dash is a finite set. So, therefore, there exists some t not equal to s such that, so if I call this set t, no, not t. Yeah, maybe, okay, tm maybe. This implies that this tm contained in k dash is a finite set. So there exists some t not equal to s such that m power t is not equal to m power s, and therefore this m power t such that this m power t 1k will be equal to m power s 1k. Okay, so this will imply that m power t into, 1k minus m power s into 1k will be 0k, right? We are subtracting the same thing. And depending on whatever this, so without loss of generality, we can just assume this t is greater than s. So this will be m power s into m power t minus s 1k minus 1 into 1k, and this will be 0k. So this, note that since we are in field, so now everything, this we can look at it as multiplication in k, and since we are in field and m is non-zero, this m power s must be, so what does this imply? This is 0k or m power t minus s into 1k minus 1k will be 0, right? And so this will imply, since m is non-zero, this implies this m power s is non-zero, right? This is still like this. We can take, does not matter. The reason being m power s 1k. Uh, For this, since m into 1k is non-zero, this implies this m power s1k is non-zero. I'm taking multiplication. Okay. So this implies that m power t minus s into 1k is equal to 1k. And since this is 0, I will get m power t minus s minus 1 into 1k into m into 1k. This will be is equal to 1k. And therefore, I get that, therefore, we get, and this is precisely the multiplicative inverse of m1k in the k dash. Therefore, m power t minus s into 1k is a multiplicative inverse of m into 1k. Is that okay? Any doubts here? Any doubt here? How this is happening, or is this clear? We just use the finiteness of k to prove this. Okay, I just assume that you understood. If not, please unmute or ask in the chat. I will try to explain. Now, so this is what we had to prove. So this also, therefore, uh, from 1 to 7, whatever we proved, we get that k dash is a subfield of k. Okay, and that's it. So let's go to the second question, that there exists the smallest positive natural number p such that this p into 1k is 0. And we also have to prove that this p is prime here. Okay, and once we get that, we will get that this k dash is precisely this set 0, 1k, I mean 0k, and so on. Okay, so let's try to prove that. The B part, to show that there exists smallest p such that p into 1k is 0k, and to show that this and this p is a prime. Okay, any idea how we can show this? And how to proceed to show that there. First of all, see, they are saying that there exists smallest. So we have to show the existence. Like, to show that something, the smallest of something exists, we first have to show that such kind of existence of such number is possible, right? To show that the characteristic is there, we first need to show that there exists some number. When I add my 1k, suppose that number is t times, it becomes 0. I need to have existence of such t in the first place to start proving that such number exists. Okay, I mean the smallest of such number exists. So let we know that, I mean, just for the sake of notation, this means adding this 1k p times, as we have defined before also. This is adding this p times. So existence of P, existence of P. So since K is finite, if I take again this 1K, 2K, oh sorry, 1K, 2 into 1K, 3 into 1K, so on up to some n into 1K in K. Okay, so it so there then when I take this, then since when I take this, since K dash is finite, these elements, the elements must repeat. Okay, I mean, see this set 2 into 1K, 3 into 1K, n into 1K, and so on. This, what we say, this is contained in this K, which is finite. And so if this has to be finite, if this is finite, then there must be some two integers, m and n, such that this m and k must be is equal to 1 and k. So therefore, there exist m and n in Z such that, or we can also write n such that this m1k is equal to n1k, right? So the moment I have this, I can take this, then m minus n 1k is equal to 0. Right, because since this is 0, this implies m into 1k minus n into 1k is 0, and this will give me m minus 1 into 1k is 0. So at least, so this m minus n, since, and we can also take this such that m not equal to n, and this happens. So since m, and also we can assume that m is greater than n. So since n minus n is greater than 0, such a positive integer exists. Okay, and since we are looking at positive integers, we can take smallest of that using a well ordering principle, that every non-empty set. So we can take this set, that set of all, since exist m minus n, so set of all t in n such that t into 1k is 0. And this is non-empty since m minus n belongs to this t. Okay, and then the smallest element of this of t is our required positive integer. Okay, therefore smallest element in t exists. And now we have to prove. So existence is clear. Now we have to prove that this p is smallest. Okay, so there were two questions, that there exists smallest p such that this happens, and now we have to prove that this p is prime. So now we have to prove that this p is prime. Okay, so since uh, Oh, so P is prime, we have to prove. So we will do that. Suppose that P is not prime. Suppose P is composite. So this implies there exist A and B in N such that AB such that P is equal to AB. And note that we are assuming that composite, P is composite. So this A and B, we can assume that none of them is equal to 1. Okay. So this will imply that P into 1K will be AB into 1K, and this is A1K into B1K. Okay, and this A1K into B1K is 0 now. And note that this is multiplication in field. Okay, and so this implies if the product of two elements is 0 in the field, then one of them must be equal to 0. Or B1K is 0. So either of this is true. And if A1K is 0, this will contradict the fact that P is the smallest with P into 1K is 0. And similarly, if B into 1K is 0, this will again contradict the fact that again P is the smallest and P1K is 0. So in either case, uh, we are arriving at the contradiction. So this implies that this is not true. Therefore, our supposition is false. Hence, P must be prime. Okay, any doubts here? I mean, this we could prove because P is smallest. Okay, this P being smallest actually playing a role here because we assume P to be smallest. Because any integer, I mean, we if P into C, if P into 1K is 0, then this will imply 2P into 1K will also be 0, right? Because this will be what? 2 1K into P1K. This will be 2 1K into 0K. And this will give me that this is actually 0K. So in that case, such composite, so if I'm starting with 2P, that or that P or whatever you want to call, if I'm looking at 2P as element which is giving me that multiplied by, if I call this S, if S is equal to, so if I'm taking at this element S into 1K is 0, then for this S, this composition is possible, 1 less than equal and 1 less than AB less than P, at least one of them. Okay, and we do not want such kind of expression. Okay, I mean, yeah, 1 less than A into B less than S. So this taking 2 and this P, both of them are less than S, and such decomposition of this S is possible. But since we are taking this P as the smallest element, uh, it's not possible to have such uh, decomposition of P as product of two integers. And that's why we could prove that it is prime element. Okay, and now the final part of this question. Yeah, I mean, this also we need to prove, right? So therefore, and since we know that P of 1k is 0, we will show that now to show that the final part, that this k dash is in fact 0k, 1k, 2k, 2 1k, and this p minus 1 1k. And how to prove this? See, if I take any value, see pk is p into 1k is my 0k, and for any element p plus some n 1k, for any integer n in this, we can always write this n as pq, q into, yeah, pq plus r, where this r is between 0 and strictly between p. And the moment I have this, then this n into 1k will be this p into q 1k plus r into 1k, right? So this now becomes 0. So therefore this n 1k becomes r 1k. And r is between 0 to p. So this will imply that this n 1k belongs to this set. So if I call T is equal to this set, this is contained in K dash. So then for n into 1k in K dash, I get that this n 1k belongs to T. So therefore, this K dash is contained in T, and from both these equalities here, let me just use this one, from these two imply that K dash is equal to T, that is this set 0k, 1k, 2 into 1k, and P minus 1 into 1k. Is this okay? Okay, and note that uh, all these elements are distinct because if mk is equal to nk for 1 less than equal to, sorry, 0 less than equal to mn less than equal to or strictly less than p, then this m minus n, and without loss of generality, so m into 1k, we can just assume this strictly less than, then this m n minus m 1k will be 0, and this now will be element less than p again, and this will again contradict the minimality of p, so such thing is not possible. So all these elements are distinct, so precisely we proved that. So first of all, we proved that this k is equal to this set, and every element of this set is now distinct, and it contains precisely p elements. So therefore k dash, this is k dash, okay, k dash has p elements, and this is what we wanted to prove as a second part. So now the third part, that this k, the original field, has cardinality some power of p. So we have to show this, and where this n is dimension of k over k dash, okay. So we'll see how to prove this. that we have to show that Q is equal to P power n with n is equal to dimension of K over K dash. And this Q is the cardinality of K. So note that this Q, cardinality of K is Q and cardinality of K dash is P. Okay. So note that so since K dash is a subfield, K dash is a subfield. Okay. This this implies K dash is a field again. Not again, I mean K dash is a field as well. So every subfield is a field to start with. So since this K dash is a subfield, K dash is a field in itself. So we look at K as a vector space over K dash. Okay. And how the scalar multiplication there, I mean this m into 1k into some x for x into k and this m1k into k dash. This will again belongs to this m into 1k into x. This will be element in k because this, I mean, this is normal multiplication in k. Multiplication in k where m1k is an element of k. Though this is element in k dash, we are now looking at it as element in k and then we are taking the multiplication. So that's it. And since k is finite, it is finite dimensional vector space over k dash. So this multiplication gives me vector space structure of k as a k dash vector space. Okay, and but again k itself is a finite vector space. I mean, yeah, I mean it has finite elements. So if it has any basis over k dash, it will be finite basis, and that will make my k as a finite dimensional vector space over k dash. Okay, so let let just a second. So let n is equal to this dimension of k dash over k. This is what this is there. I mean, this I'm not calculating. I have this information since I'm defining this n as dimension of k over k dash. Since k is finite dimensional vector space over k dash. Okay, so this n I'm defining as a dimension of k over k dash. So then elements of k and with basis, suppose with basis this b1 to bn. Okay, so any element of k, the elements of k as k dash vector space will be of the form this A1 B1 plus A2 B2 plus AK BK, where these AIs are in K dash. So how many such possibilities are there? Each of this element has P possibilities, right? Sorry, this is N. B here is N. So since K dash has P elements, there are P choices for each AI. For each AI, and this will for each AI, and we have to choose N such, and each AI, and since there are N elements in the basis, this cardinality of K will be this P for each AI. There will be multiplication when I'm trying to calculate the choices for this. So this P into P, this will be N times. And this is precisely P power N here. The P choices. So yeah, P elements. This P is cardinality of K dash. So any doubts here? I mean, I hope you know how many choices this will have. We have to, I mean, whatever choices this AI has, multiply, and we have to multiply because uh, randomly. So this is like I have this N boxes to fill, and for each box I have this uh, P choices. So there are total P power N choices. So, but that's precisely what will give me the entire set K dash. These are precisely the elements of K dash. Sorry, these are precisely the elements of K. So cardinality of K will be the choices of this AIs here. How many possible choices of this KI here? And that is P power N. So therefore, cardinality of K, which was Q, is actually P power N, where this P is cardinality of K dash, and this N is precisely dimension of K as a K dash vector space. And that's what we wanted to prove here, if you remember. Yeah. So Q is this P power N, and N was this dimension of K as a K dash vector space. So any doubts here? Yes, it's counting rule. Yes. This P power N which we got here is actually obtained by the counting rule. Uh, I hope it's clear. Mhm. Just a second. Now we'll go to next question. Yes. Let me just check. Yes, yes. This is question 5.5 from the assignment sheet. And yes, it would let's go to take sure. Yeah, sure, we can do that towards the end. Is that okay? Or you have any specific question, you can ask it right now. I mean, you can write the question and I'll try to answer that. Meanwhile, I'll write the question for the next question. Or if you want, you can just unmute and ask the question. I mean, you can ask the question anytime, anything related to the course. I'm finding lecture for this course difficult to follow and I haven't given up yet. I want to do one. Okay. So, what I would like to ask you is like, how much linear algebra you know? I mean, are you in what course right now? So you are asking about the books to follow for this course, right? So if you give me that idea, then maybe I can recommend you the book accordingly. Because this course is uh, um, I mean, we are looking at linear algebra from very different perspective than normal books which we follow. I mean, what mostly they do is they just define vector space following those 8 or 10 properties, and they derive theory around it. But we are completely looking at it through uh, very different way. So it might be difficult to follow. Yes, I agree. But yeah, if I know what's your background, then I can help you better way uh, in suggestion of the book. So maybe you can write that in the chat. Then I can suggest you accordingly. If I don't know what to suggest you right now, I'll just look for you and I'll maybe put that up in the discussion forum, or you can email me. Yeah. Is that okay for now? Okay, so let us try to do this next question. Let V be a, this is question 5.5 from the assignment sheet. So let V be a finite dimensional K vector space and U be a subspace of V. So let U1 to, okay. Oh, so, okay, okay. I have, so let me just copy all this and then I'll suggest you maybe in next week class, or maybe you can raise the same question in the discussion forum and I will answer that there. Okay, so everything you have learned, I have copied it and I'll suggest you both accordingly. Okay, sure. So, yeah. So this is the question we are trying to solve right now. So we have this V finite dimensional vector space again, and U be a subspace of V. Subspace of V, yes, and then let U1 to UM be the basis, be a basis, okay, be a basis. It's always the dimension and a basis of U, and let U1 to UM and UM plus 1 to UN be the extended basis of V. And we have to show that X is equal to A1 UN, sorry, AMUM plus bm plus 1 to um plus 1, yes, plus bn un belongs to V is an element of U if and only if the coordinates bm plus 1 is um plus 1 star x and bn is equal to un star x of x with respect to the basis u1 to un of V r0. So basically what we have to show that if so understand the question. So understand that this element, so we are given this basis u1 to um of u. Okay, and then they are writing this element x as some linear combination of a1 to am and and bm plus. So x is, so we are extending this to basis of V. So dimension of V is n, dimension of U is m, and from m, so we know that every basis of a subspace can be extended to the basis of a vector space, the whole vector space. Okay, we can choose the elements which are linearly independent uh, from for the original basis of the subspace which we started from. Okay, so what we had was m elements, and now we extended it to n elements, and then they are saying that this x belongs to you. Now this x belongs to you if and only if this bm plus 1 to bn are 0. This is what uh, we have to show. Okay, and this is the way we often characterize the, what we say, subspace of a given vector space. Okay, and what I said here is that, so I hope you know what basis means, right? Basis has two elements. First of all, it spans V. So basis of U over K means that it has two properties. First of all, it spans V, that if basis, let me take this. So it has two properties. First of all, that U is the span of this U1 to UM, and second is that this U1 to UM are linearly independent. And this span is okay, but this linearly independent can also be looked at it as that no proper subset of B can generate the subspace U. And we can see that from the exercises which we did during last tutorial. I hope you remember something like this. this we took x1 to xn and x, and we showed that x is linearly independent if and only if x does not belongs to, if you remember this, that this is linearly independent, this set is linearly independent if and only if this x1 to xn are linearly independent, if you remember. Oh, let me write it properly. Linearly independent, and this x does not belongs to, if I remember correctly, it was kx1 to kxn. I mean, this is just expression of writing the field and subspace generated by x1 to xn and so on. But this is what we saw, and this is what gives me that this entire set is linearly independent. And so the way to look at it as something being basis, when we say, so we can either say that these are all linearly independent element, or no proper subset of this set can generate the entire space. So the other way to say that basis is a minimal spanning set. So when we say minimal spanning set, it means that no proper subset of that set can generate the entire space. So spanning set could be anything. So for example, if I have this here, I can just write this um plus u1. This will still span my set u. This will still span my subspace u. But when I say that this if I'm looking at this set b dash, if I'm saying that this b dash is a basis, then it won't hold, because I can remove this element plus 1 to un, and still it will give me my subspace u. The span of this remaining set will give me the span of u. And the second way to look at it as that this is again not linearly independent, because this if I look at this won't be linearly independent, because I can have this, right? 1 minus 1 u1, so on, minus 1 plus this plus u1. And this is some non-zero linear combination which is giving me 0 again. So this is not a linearly independent set. So the linear independence can also be looked at as the minimality of generation. I mean, the minimal set which would generate my subspace. Okay, I hope that is clear what I said so far. So let us look at how to solve it. So let us start. So as we are given, let V be a vector space, and let dimension of V over K be n, and let U be a subspace, and dimension of U is M as given, and basis of U is u1 to um, and basis of V is u1 to un. Anyone said it? Okay. u1 to um plus 1 to un. Okay, so for x in V, so I'm saying that I'm choosing x in V, and then this x will have, since this is basis of V, this x I can write it like this. We know this um plus 1, sorry, am plus 1 plus 1 plus an un. This is so far just basis property of this set, and X is some element of V. Okay, and since we have this extension of a basis, this A1 AM and this BM, oh sorry, this they are noting as BM plus 1. Bn are coefficients, okay, or are in K. Okay, so the dual basis U1 star, UN star will be there in V star. Okay, and it satisfies that. So corresponding to each basis element of V, uh, we have corresponding dual basis in dual space. That's what we are talking here. And this this is such that this Ui star Uj is delta Ij, and delta Ij is this function such that it is 1 if I is equal to j, sorry, I is equal to j, and it's 0 if I not equal to j. Okay, for all those 1 I comma j less than equal to n. And then that's it. This uk star of x will be ak for 1 less than equal to k less than equal to m. And then this uk star of x will be bk for m plus 1 less than equal to k less than equal to n. And now we need to show that this bm plus 1 to bn is equal to 0 if and only if x belongs to U. Okay. So first implication. So wait, the first implication x. Okay, I'm proving the other way around. The second implication is that assume x is in U. Then since so x is some summation C1 U1 plus CM UM. Okay, where this C1 to CM belongs to K. Okay, and since this is basis, the expansion is unique. So by uniqueness, of the expansion of the basis expansion in V, this x must be C1 U1 plus CM UM. So this, when I'm writing this, I'm looking at this is happening in U. This is happening in U. And now this will happen in V. And this will be 0 UM plus 1 because the extended basis is again a basis, and that basis again will have uniqueness in the expression. Okay, so every element in the vector space is what we say is has unique basis expansion. So if I'm saying that something is a basis, if I want to write a linear combination of any element with respect to that basis, then that expression is unique. Okay, and even that is what we in fact used here as well. This, when I'm saying that this B1 to Bn are all independent. In the previous question, are basis element. Uh, and we just say that AI has P possibility. And we just said that the cardinality of K will now be P power n. We did not check here that none of them are coinciding. So, for example, what I'm saying is that this A1 B1 plus A n Bn is not equal to A1 dash B1 plus An dash Bn when AI uh, AI not equal to AI dash for some I. Okay, the moment I have different coefficients, every time I am getting different element. That's how I could write this here. This is because of the uniqueness of expression. When I'm every element is uniquely determined by the basis, uniquely expressed as a linear combination with respect to given basis. Okay, and that's why I could directly say that just because AI has p possibilities, there are n, so there must be p power n elements, because no two combination of AI would give me same element. Each time I have different possibility of AI, I will get different element every time. And that's how I could conclude this here. So, okay, sorry. That's how I could conclude this here. And that's what again we are using here, that since this has expression like this expression will continue here uh, in this form. And since x had this expression where coefficients of ui were ai, I will get that. Therefore we get that u this bm plus 1 is equal up to bn all or 0. The coefficients of all um plus 1 to un are 0. Is this okay? This is because of the unique expression of basis. Any doubts here? No, right? So let's prove the other part. That assume that um plus 1 star x into un star x to be 0. Then I mean, this is pretty easy, because then all this bm plus 1 into bn is 0 in the expression, and then x is anyway, we have this expression, right? An. I mean, this is actually u1 star x a1 star x am, plus since this is 0, I get 0 so on, and 0 un, and this is some u1 star x a1, sorry, this is u1 star x and this is anyway 0, and this is just some linear combination of elements of basis of u, so this must belong to u. So this linear combination belongs to u, therefore x belongs to u. Is that okay? So let's try to, if there are doubts, please let me know. Otherwise, we'll move to next question. So this is first question, that we have to check true or false. Uh, the vectors 1 1 1 1 2 1 1 1 1 1 n form a basis of Rn. We have to check whether this forms a basis of Rn. So first of all, there are n elements. Okay. So property of basis, there are many ways to look at basis. So for basis, we have two properties to satisfy. First is it generates what we say, it generates the set. The span of given elements generate the set, and span of given element is my set Rn. And secondly is to prove the independence. But we also know that if we know the dimension of a given vector space over the base field, then every basis has that cardinality. So we know that dimension of r power n over r is n, and there are n elements here. So therefore, it is enough to show that this set 1 is linearly independent. Okay, this is something which you can note or remark, that if dimension of v over n over k is n, then first that if v is spanned by u1 to um, then this m will be greater than equal to n always. Okay, any smaller set of cardinality less than the dimension can never generate my space. Okay, and if v is span of u1 to no if u1 to u, let us say k, is a linearly independent set, then this k must be less than equal to n. Is it easy to is it okay to see, to assimilate that these two actually hold? These two are properties of finite dimensional vector space. You can check. Okay, and you can try to prove this as well. You will always find this. You can easily prove this. So what we have here now is that this is set of cardinality n, and if I prove that it is linearly independent, then I'm done. Okay, so to show that, we will show that this set, let us call me this, let this set be called T. We show that T is linearly independent. So suppose let A into 1, 1, A1 into 1, 1, 1 plus A2 into 1, 2, 1 plus AN into, this is how we prove linear independence, right? We start with some linear combination and we prove that each coefficient is 0. Okay, so this will imply what? A1 plus A2 plus, okay, so let me write this. A1 plus A2 plus so on up to AN, comma. Second one will be A1 plus 2A2 plus AN, and last term will be A1 plus A2 plus NAN. This will be equal to 0, 0, 0. And now what I will have here is this 1 into A1 plus 1 into A2 plus 1 into AN is 0. 1 into A1 plus 2 into A2 plus 1 into AN is 0. And this 1 into A1 plus so on plus N into AN is 0, right? So what we can see, this is system of this is homogeneous system of linear equations, right? And if I want to write this in matrix form, it is this matrix 1, 1, 1, 1, 2, 1, 1, sorry, 1, 1, n into A1 to AN is equal to 0. Right? So in case of homogeneous system, if I want to show that something has unique solution, what we need to prove? We need to prove that, if you remember, I think last to last lecture which we did, we need to prove that for homogeneous case, there are only two possibilities. Either there are either there is unique solution or there are infinitely many solutions. So there is unique solution only when the coefficient matrix or this matrix here. So in case of AX is equal to 0, there are only two possibilities, either unique solution or infinitely many solutions. Unique solution if determinant of A is non-zero, and infinite solutions if determinant of, it's actually like this, determinant of A is 0. Okay, we have these two possibilities. So we have to check whether determinant of this matrix is 0, non-zero or not. Right? And what do you think? What will be the determinant of this matrix? Okay, so let us try to do this. So we have here, I'll just show you, okay, we have to find the determinant. Okay, so we don't have to convert the entire matrix into what we say. So I'll just show you two rows and then we can see that the determinant will be non-zero, because see, if I do this, R2 minus R1 and all the way Rn minus R1, then I will get this 1, 1, everything here. This is 0, 1, 0, 0, 0, right? This is 0, 0, 2, and rest 0, 0, 0. And right, if I'm making any mistakes, please let me know. This will be 0, 0, so on, and this will be n minus 1, right? And in one go, this becomes upper triangular matrix, right? And then determinant of this matrix is, this is my A. So determinant of this is suppose A dash. So determinant of A is equal to determinant of A dash. And this is just 1 into 2 into whatever it is. 1 into 2 into n minus 1. So 1 into 1 into 2 into n minus 1. And this is non-zero. I mean, yeah, this is non-zero. We can assume just that n is greater than equal to 2. Does not matter. Product of diagonal element. Exactly. So determinant of A will be a product of diagonal of A dash. Okay. So therefore we get, and which is non-zero. This is non-zero. So therefore, this system, if I call this system epsilon, therefore epsilon has unique solution. And what is the solution? What is the solution which always exists in case of homogeneous system of generator? Sorry, homogeneous linear system of equations? 0, 0, 0, right? So, namely, 0, 0, 0. Okay, so this is unique. So therefore, this A1 to AN is A1 is 0 and AN is 0. Okay, therefore, this expression, hence we get that 1, 2. I mean, the matrix had very good form. That's why we could get it, but that's okay. It does not matter. Is linearly independent. And so this T is linearly independent with n elements where n is dimension of R over Rn. Therefore, T forms a basis. And if you want to know in general how this also generates, so note that if I have some element R12, so if I take x in Rn, okay, so it will be of the form x12 xn, right? So I note that A determinant of A is non-zero. Determinant of A is non-zero. So for this x, I have this expression x1 again 1, 1, 1 plus a2 into 1, 2 and so on plus an into 1 up to 1n, and this I will equate it equal to xn. And this becomes this system 1 1 1 1 2, sorry, 1 2 1, so on 1 1 n. Okay, and this is a1 to an, and this if I equate to x1 to xn, then we know what solution this a1 to an is. I told you last time, if I take this a multiply by a inverse, because a inverse we can find, so determinant of a is non-zero, so a inverse exists, and a into a inverse, and a inverse x1 to xn. And so precisely this becomes identity into a1 to an, and so this is a1 to an into a inverse x1 to xn, and whatever this a1 to an we get by multiplying this a inverse by x1 to xn will be, this will be again unique, right? This will be unique because for a, since for a inverse is unique, and since x we are choosing, this x1 to xn are fixed anyway, so this expression a inverse x1 to xn is again unique. Okay, and so this a1 to an whatever we get for this particular x here, which we chose from Rn, is unique, and that is my unique expression of this element x in terms of this basis. This basis t is equal to 1 1. I'm just writing this. I hope you understand what I'm trying to uh, point out here. Okay, this is unique expression. So uniqueness of this expression, and I mean, so instead of this, if you take any n vectors linearly independent, to check whether they form basis or not, we have to first check whether they are linearly independent. So what you can do is you can form such matrix of those vectors, check its determinant. If it's 0, then it won't be a linearly independent uh, set. And once it is linearly independent, this determinant will be non-zero, and it will give me the expression in terms of basis of those elements. Is that okay? I mean, I'm just I mean, this was extra, was not asked in question, but I was just giving you information that how exactly you find those coefficients here in this case. Okay, and this question, this second part, is what we actually discussed previously. So this is question, I don't remember exactly the number. Maybe this question 4. Question 4, that in every finite field K, there exists a unique prime number P. So this is true, okay? I forgot to mention this was true and false question, and this is definitely true. And this question is again true or false. We have to check true or false, but okay. So number P and a unique subfield K dash of the cardinality P. And we have to check whether true or false. Is this true? From what we did here earlier. So we already, so from question 1 which we solved, we know that K dash is equal to this M into 1K such that M belongs to Z. This is my field, unique field. This is unique the way it is defined. It has exactly P P element. Cardinality of K dash is P. And we in fact proved that cardinality of K is P power n, where n is dimension of K as a K dash vector space. So this is true because see the explanation as in question 1 discussed before. Okay, so what we did in first question is exactly what they are asking here in this question. So any doubt here?
That seems okay.
Okay, so let's go to the third part of this question. I think question 5. Let P be in CX. Sorry, not this one. Question 5. For which pair A comma B in K square? K is arbitrary in fact. Yeah, V is A comma B and V dash is B comma A in K square. Form a basis of K vector space K square. Uh, can do you have any guesses for this? So question is, when does AB and BA for A comma B in K, when does AB and BA forms a basis K basis of K square or K2, whatever you want to call? This is the question. And what is your guess for this? So we want to check. See, there are two elements again, and we have to check something is a basis. So the only thing we need to check is whether they are linearly independent or not. And to have the linear independence here, we will have some conditions on A and B, and that's exactly what we have to find here. Okay. So we need to check. Okay. So let's suppose consider XAB plus YBA is 0, 0. Okay. So this will give me XA plus YB, comma YXB plus YA is equal to 0, 0. And if so this is XA plus YB, or let me write this, AX plus BY is 0, and BX, why I'm writing it like this is because this is my matrix, AB, BA, XY is 0. I need to find XY. And when will this be 0? I mean, sorry. I want this to be non-zero, right?
Yes.
Yes. So this imply we want. So if I write this as AX is equal to 0, we want A to be invertible. So that is we want A square minus B square to be non-zero, right? That is determinant of A. I want to be non-zero. That is A square minus B square I want non-zero. So this imply what? Either A minus B I want non-zero and A plus B I want non-zero. So what are the possibilities for this? If I want both A and B to be non-zero, what it will be? A minus B and A plus B to be non-zero.
A should not be equal to B.
Yes. If I want this to be non-zero, so this will imply A must be not equal to B and A must be not equal to minus B. This,
Yes.
yes. So these are the
You can.
only conditions. Other than that, we will always have it to be basis. I'm still confused why they want A to be not equal to minus B. Because, so for example, if I take 1 and minus 1, okay, this is my A and minus 1 B. Then BA will be minus 1, right? This will still form basis, right? Or no?
Yeah, it is. Determinant of this is also non-zero.
Yes, exactly.
No, but these conditions must be hold together, or it is independent. I mean, A is not equal to B. At the same time, A is also not equal to minus B. It is not or condition.
Yeah, both, right? Yeah. Yes, I mean, yeah. The moment I have A not equal to B, yes, exactly. Yes, this both, so this is to avoid zero. So both must satisfy together because it
Hmm.
should satisfy zero. Otherwise, it's okay. We want both to be true. Hmm. I hope this is okay, right? I mean,
Any other value other than this will give the unique solution, and therefore we can say in any other form of A and B can form a basis.
see, you are saying that this must be or.
I am no, I am not saying this must be and
No,
then
no.
only,
Yes,
uh,
sir. Yes, sir. You are saying
this must be a and condition, then only okay.
it must be and, right? I mean,
So if we just write a square minus b square is equal to a minus b dot a plus b.
and if I want that to be non-zero, then this is logically correct. Because if one of them is zero, then product will be zero.
Yes.
Yes. So this has to be there. Uh, okay, I mean, we have arrived at this conclusion following all the logical possibilities. Yes. I mean, you can check A not equal to B and A not equal to minus B. Yeah, you can check. But so far it looks fine. But this definitely also gives me basis. So forget about this. The base for this, I mean, entire thing is that determinant of this A, that A is this A, B, B, my B, A, must be non-zero. Determinant of this A must be non-zero. This is my main condition. I mean, forget about this dependent and independence of A. A being minus A minus B, B minus A. This must be the main condition which it should follow. Okay, so let us move to next question. We can find the coordinates. So this 5.4, if you look at the question, it again coming from, so let me just write this question. This is, I think, question 6 which we are discussing. That is question 5.4 from the assignment. This is again that let K be a finite field of cardinality Q, and we have to prove that K is a vector space of dimension n has exactly Q power n elements with. So this is K is a finite field of cardinality Q, and prove that K vector space of dimension n has exactly Q power n elements is because again the property which we use, the uniqueness, is followed from this. So K is a field, so let V be a K vector space of dimension n. So yes, suppose not suppose V basis of V be A basis of V be A1 to V1 to Vm, Vn to Vn, and we have cardinality of K as Q, right? So again, any element in, as we saw in V, any element X in V will be something like this: A1 V1 plus An Vn, and each, again, the same choices we had. The choices, there are few choices for each AI, and therefore and uniqueness of expression for basis gives us that this cardinality of K, cardinality of V will be Q power n. So finite dimensional vector space over finite dimensional field, finite dimensional vector space over finite cardinality field will have finitely many elements, precisely this many elements. So this is cardinality of K power dimension of KV. This is exactly what my V is. Cardinality of vector space is what is asked. Okay, has exactly Q power n element. You can use this in whenever you want to use. And this question, I will just, we are almost there. Okay, we are about time, but let us prove this one. This questions which is given, this is question 5.2, no, 5.3. That determine the coordinates of the vectors I comma 0 comma 1 plus I comma minus 2 plus 3i with respect to the basis v1 is equal to 1 plus I comma v2 will be 1 comma 1 plus I of the C vector space. So this is similar to what we C vector space C square, where I is in, we know that what I is. So we have to determine the coordinates. So what exactly we have to find is coordinates of the vectors. So what we need to do is we have to find I0 is A1 1 plus I comma I, plus b1 into, or let me write AB, 1 comma 1 plus I, and 1 plus I comma minus 2 plus 3I is equal to C 1 plus I comma I plus D1 plus 1 I, and so in short we have to find this ABCD. Okay, this is our task. This is our task for this question. We'll just do the first one and then we can stop. What we have here is, did I write anything wrong here? 1 comma 1 plus I. So this is 1 plus I, 1 plus I into AB. This is I into 0. Or we can just simply solve this system. 1 plus IA plus IB is equal to I, and C plus, no, sorry. Am I correct? No. Here it will be 1. 1 or I? No, it's I. This is correct. This is I. 1 plus. Let me just write it properly, okay? A into 1 plus I plus B into 1, comma A into I plus B into 1 plus I. I want this to be equal to I comma 0. So this is A 1 plus IA plus 1 into B is equal to 0. And this is I into A plus 1 plus I into B. This I want to be 0. And we have to just solve this system of equation, and then whatever we get A and B as will be the coordinates of this. So shall we, or if you want, you can just find the inverse of these elements. So for 2 cross 2 elements, I hope you know the inverse, 1 by determinant, and just switch the, so for this matrix 1 plus I, 1 I, and 1 plus I, if this is my A, we can check determinant of A is, whether determinant of A is what? 1 plus I square minus I. So this is 1 plus 1. This is 2I minus I. So this is 2 minus I. So this is anyway non-zero. So A inverse will be 1 by determinant of A. And then this 1 plus I, they are actually switched. And then this will be, I think, minus 1 minus I, if I'm correct. And this, if you do, so this AB will be precisely this A inverse into I into 0. Okay, so B must be, when B is straightforward 0, and A will have some expression here. Is that okay? I mean, I do not want to go into the detail. This is just solving system of equation over C, okay? Solving system of equations over C. Is that okay? Or any doubts, please let me know. And similarly, you can do for this C and D also. I mean, once you have inverse of this matrix A, just multiply that matrix to whatever you want on the left hand side. So even for, so this, for C and D, it will be similar. So CD will be this A inverse into whatever we want here. 1 plus I and 1 plus I, and this is 2 minus 3I if I'm not okay. If this is what here. So whatever basis we have, just try to, so whenever we have system of equation, the basis given, try to find the inverse of corresponding matrix which we obtain. And whenever we want to find such expressions, just multiply that A inverse to whatever element we have here, and that will give you the coordinates. C and D for coordinates for X, we get. Is that okay? I mean, just overall. So once we have the idea of A inverse, we can find coordinates in one go for any given uh, element X from the vector space. Is that okay? If there are any doubts, please let me know. Otherwise, we can stop.
Yeah, looks like okay.
Yes, it looks okay so far. If it, even if you later on, if you are looking at the notes and if you find any errors, please let me know so that we can discuss those next time if there are any mistakes. And also, whatever there is, please ask in the discussion forum or ask in the this lectures is fine. And about the book suggestion, I will definitely look for it, and I'll suggest a book which suits the course of, the material for this course and so on. Okay, if there are no doubts, thank you, and let's meet next week. Yeah.
Thank you.
Thank you, sir.